I'm Shan Huang from East China Normal University. Today I'll talk about robustifying debug location updates in LLVM while control flow conformance analysis. When compiling user programs with flag -G, compilers would generate a critical combination metadata named debug information along with the binaries. The generated debug information enables a variety of important program analysis techniques like debuggers, profiners, sanitizers, tracers, and coverage collection. Due to its usefulness, modern software projects usually recommend adding the -G flag to improve the quality assurance support. Debug location information, one important kind of debug information, maps low-level instructions to the statements in source code. For example, assuming we have the following C code and compile it with the flag -G, when debugging, the debugger could show where the program reaches, reading the debug location information embedded in the binary, and show the corresponding source code while a simple mapping process. Another example is that when running programs instrumented by address sanitizer to find memory bugs, address sanitizer uses debug location information to report where the program crashes. In LLVM, debug location is a kind of metadata attached to LLVM IR instructions. Here is an example. In the same C code, the subtraction expression A-1 in line 3 is compiled to this sub-instruction in LLVM IR. If we enable debugging compilation, this instruction would be attached with an additional compilation metadata, which is the debug location. It's easy to see that the first two fields of the debug location map the instruction back to line 3 and column 17 in the source code. To use such information to perform reliable program analysis, we wish the mapping to be accurate. However, compiler optimizations may invalidate debug locations. Consider the function recursion in the C code. I'll show you how compiler optimization invalidates debug locations on the control flow graph of its LLVM IR. The multiplication expression in line 7 is compiled to the LLVM IR instruction mall in the basic block if.else. In this and the following examples, we use the line number in the source code to denote the debug location attached to the instructions. Assuming we optimize this multiplication by replacing it with an addition, a new instruction add is created to replace the original instruction mall in the AR. And the new instruction add it has no debugging location attached, which is denoted as line 0. Unfortunately, after this instruction replacement, there is a debug location loss in this program because the debug location of line 7 is discarded along with the deleted instruction mall. As a result, debugging or profiling the line 7 become infeasible. To avoid this debug location loss, the debug location attached to the deleted instruction could be preserved to the semantically related new instruction, which means we copy the debug location of the instruction mall to the instruction add. This process is called the debug location update in LLVM, which is required to be written by optimization developers in optimization code. Specifically, the debug location update consists of 3 parts: the source instruction from the unoptimized program, to which the attached debug location is used for the update, the destination S' from the optimized program, to which the attached debug location is updated, and the update operation, which uses the debug location attached to the source instruction to update that of the destination instruction. Currently, there are 3 update operations in LLVM, which are preserve, merge, and drop. To make debug information in optimized programs reliable, the debugging location updates should be correct. However, manually updating debug locations is error-prone, leading to update errors that subsequently cause debug information bugs. Next, I'll give you an example. In the same C code, we can see that line 5 is in a dead branch because the value of the variable a always equals 2 when encountering the second if condition. and line 7 is thus the live branch. However, if we compile this C program with LLVM optimization tail call elimination, when debugging the optimized code, the debugger shows that the execution enters the dead branch, although the real program state is correct. And this is a debugger information bug caused by a debugger location update error in optimization tail call elimination. I'll demonstrate the root cause of this bug also on the control flow graph of the function recursion. After the front end, the addition expression in line 5 is compiled to the instruction add with a debugger location pointing to line 5 in the if.then2 block, which is the dead block. After the optimization, the control flow graph changes, but the branches remain unchanged. The tail call elimination clones a new instruction add prime from the instruction add and inserts the new add prime to the live block if.else. Meanwhile, the debugger location of add is preserved to add prime. However, this is a debugger location update error. Because when the program executes along the path gamma and encounters end prime, the debugger reads the debugger location pointing to line 5 and shows that the program execution enters the dead branch, giving the misleading information to users. Such misleading information severely impacts the reliability of the techniques and using debugger locations. Recently, several works leverage testing to find debug information bugs. They use debuggers to debug both the unoptimized program and the optimized program, comparing the debugging traces. Any inconsistency indicates a debug information bug. For example, when debugging the unoptimized code, the debugger never shows the deadline 5. However, when debugging the code optimized by tail call elimination, the debugger shows that the program execution reaches the deadline 5. Thus, this inconsistent debugging behavior indicates a debug information bug. Although they are effective in finding bugs, lacking the knowledge of the optimization process, they cannot help locate and fix update errors. In this work, instead of detecting debug information bugs, we propose a robustification technique which finds and fixes debug location update errors. In addition to the unoptimized and optimized programs, our robustification technique also analyzes the LLVM optimization process, determine the correct updates, which is then used to find the update errors and generate patch skeletons. Central to our robustification approach is determining the correct debug location updates in LLVM optimization process. So for robustifying debug location updates in LLVM, there are two unique challenges. First, how to identify source and destination instructions. Second, how to determine the correct update operations. To tackle the first challenge, we need to understand the destination and the source instructions. In the previous example, we showed an update using the update operation preserve. In this example, we can see that the source instruction as from the unoptimized program is that the source is the instruction providing the debug location for updating. The destination instruction S prime from the optimized program is the instruction semantically related to the source instruction. For example, the destination instruction is a replacement of the source instruction in this case. Meanwhile, the destination instruction is the instruction whose debug location should be updated. In this example, the destination instruction is a newly created instruction with an empty debug location. So when it is inserted into the IR program, it can be assigned a new debugging location. According to this understanding from the LLVM class instruction, we extract 4 categories of instruction manipulation APIs, which can capture in the source and destination instructions. To use them, we monitor the execution of the optimization process and record the instruction operands and the corresponding variable names of these 4 kinds of APIs. After identifying the source and destination instructions, the second challenge is to determine the appropriate update operations for them. To tackle this challenge, our observation is that the debug location is an update in an optimized program, and its optimized counterpart should satisfy a conformance relation, which requires no extra debug location appears on control flow paths in the optimized program. In the previously discussed debug information bug, debug location of line 5 does not occur on the path gamma before the optimization. However, after the optimization, the debug location of line 5 appears on this path. And thus, it's the extra debug location for this path gamma, violating the conformance relation. To enforce the conformance relation, we should avoid introduce such extra debug locations into paths in optimized programs. From this example, we can see that the root cause of extra debug locations is that the destination instruction add prime appears on a control flow path that does not contain the source instruction add. Therefore, we propose control flow conformance analysis to determine the appropriate update operations that enforce the conformance relation. Specifically, the control flow conformance analysis checks whether there is a control flow path which contains the destination instruction but does not contain the source instruction. If there exists such a path, the update operation is dropped. If there is not, the update operation is preserve or merge, which means we keep the debug location. Recall the previous code optimization example in which the update operation preserve is used. In this example, the destination instruction and the source instruction are in the same block, indicating that all control flow paths passing through the destination instruction must pass through the source instruction. So the check of control flow conformance analysis fails. The update operation should be preserved. In the example demonstrating a debug information bug, the destination and the source instruction are located in different branches of the same if condition. So there exists a path which contains the destination instruction but does not contain the source instruction. As a result, the update operation should be dropped to avoid introducing an extra debug location to that path. However, as we discussed in this bug, the optimization tail call elimination preserves the debug location from the source instruction to the destination instruction. Therefore, using the determined update operation drop, we can find this debug location update error. Meanwhile, the determined update operation can tell us how to fix this debug location update error. That's how we robustify the debug location updates in LLVM. We have limited the robustification technique in a tool named Mentalog. The first part of Mentalog is a standalone path instrumentation tool, which instruments the instruction APIs and the entries and the exits of LLVM optimization paths. The second part is a lightweight built-in library for LLVM, which implements the instrumentation hooks, the control flow conformance analysis, and the patch scatter generation. To evaluate Mentalog, we run it on all 80 scalar optimization paths with the corresponding regression tests and the path inputs. As a result, with the help of Mentalog, we have successfully fixed 46 update errors in 18 optimization paths using 21 pull requests. In addition, we have fixed one incorrect and one incomplete update example in LLVM documentation according to our control flow conformance analysis. You can check out our paper for more evaluation details. To sum up, we improved debug information quality from a new perspective. Instead of testing, we robustify debug location updates while analyzing both compiler optimizations and LLVM IR programs. To achieve that goal, we designed the first robustification approach, of which the core is control flow conformance analysis for determining the correct update operations. Finally, we evaluated the implemented tool Mintalog, helping find and fix 46 debug location update errors in LLVM. Thank you for listening. That's all.
Okay, we have time for a couple of questions. So then let me ask you a question.
Okay.
So this is specific for maintaining or improving the debug information because they get lost when you do optimizations.
Yes.
Does this also apply, or do you think this could generalize to other forms of metadata you might want to kind of maintain while you perform optimizations?
Okay. I think this is specific to the debug location updates in LLVM. But this approach maybe can be generalized to other compilers like GCC, which maybe they use the same mechanism to maintain the debug locations. But for other compilation metadata like debug values or other something, we need to find another way to address them. Okay.
Hey, great talk.
Okay.
Konstantinos Kallas from UCLA. So as far as I understand, the technique that you use is able to fix bugs essentially in this information preservation. Could you also see this being extended to fully automate this debug preservation, essentially lowering even more the developer overhead? Yeah.
Okay, that's a good question. And actually, I'll see. Actually, we can determine the correct update operations, but to write the code, we can do a simple skeleton translation. So we just output the skeletons, but the actual code should be written by human. So in this project, we write them by ourselves and send them to the LLVM community. Yeah.
Cool. All right. Then let's thank Shan. The next speaker can cover.